In module 2 of chapter 9, we shall learn two very important theorems on surface. First one is Misner's theorem and the second one is Theorema egregium of Gauss. From the first theorem, that is from the Misner's theorem, we shall get the concept of normal curvature. Normal curvature of a surface is related with the geodesic curvature and the curvature of the curves on a surface. So, we shall establish a relation also about the normal curvature, geodesic curvature and the curvature of curves on the surface. And from the theorem of egregium of Gauss, we shall show that the Gaussian curvature depends only on the first fundamental forms. So, let us see the two very important theorems in this module. Let us start our first theorem, that is Misner's theorem. Misner's in 1785 published a paper where he has given this theorem. And secondly, in this module we shall learn Theorema egregium of Gauss given by German mathematician Gauss, Carl Friedrich Gauss. So, let us see the first theorem and its proof. Misner's theorem. Now, the Misner's theorem states that for all curves on a surface which have the same tangent vector, the quantity kappa cos theta has the same value, where theta is the angle between surface normal and the principal normal. That means, the surface normal is a space vector and principal normal of the curve is also a space vector. So, we are considering theta is the angle between surface normal and the principal normal, and kappa is the curvature of the curve. Now, let us see the proof of this theorem, a very important theorem for the surface geometry. Now, here the curve is considered in two ways, once as a surface curve and again as a space curve. Now, if we consider the curve as a surface curve, its unit tangent vector and unit principal normal vector are denoted by lambda alpha, eta alpha. So, lambda alpha are the components of unit tangent vector and eta alpha are the components of unit principal normal vector. And we have considered this lambda alpha and eta alpha in such a way, so that lambda alpha, eta alpha and xi I is the surface normal vector and it is a space vector and they forms a right handed system. So, lambda alpha, eta alpha, xi alpha forms a right handed system. Now, as a space curve, its tangent vector is denoted by lambda I and principal normal vector is mu I, and they are both unit vectors. So, lambda I is related with lambda alpha by the relation lambda I equals to xi alpha lambda alpha. Now, taking intrinsic derivative to the above relation, we get del lambda I del s equals to xi alpha del lambda alpha del s plus lambda alpha. Now, the intrinsic derivative of xi alpha is xi alpha comma beta du beta ds. That means, we have considered the tensor derivative of xi alpha with respect to beta, and then the inner product has been done with du beta ds. Now, we shall use three theorems or three results actually, that using Frenet formulae for space curve, surface curve and Gauss formula. All these things we have learned earlier. So, using these theorems or these formulas, we have kappa mu I equals to xi alpha kappa g eta alpha plus b alpha beta xi I lambda alpha lambda beta, because del lambda I del s can be written as kappa mu I, del lambda alpha del s can be written as kappa g eta alpha, and xi alpha comma beta can be written as b alpha beta xi I. So, we get this relation that kappa mu I equals to xi alpha kappa g eta alpha plus b alpha beta xi I lambda alpha lambda beta. Now, xi alpha eta alpha will give us eta I. So, the equation 7 is coming out, that kappa mu I equals to kappa g eta I plus b alpha beta xi I lambda alpha lambda beta. Now, according to the statement of the theorem, if theta is the angle between mu I and xi I, then cos theta equals to gij mu I xi j. Now, we know that both mu I, that is the principal normal vector, and xi I, that is the surface normal vectors, are unit vectors. So, cos theta can be defined in this way, that cos theta equals to gij mu I xi j. So, now if 7 is multiplied by gij xi j, then we have kappa gij mu I xi j equals to gij eta I xi j kappa g plus gij xi j b alpha beta xi I lambda alpha lambda beta. Now, we know that chi is a unit vector. So, gij xi xi j is equal to 1, and eta I and xi j are orthogonal vectors. So, g I j eta I xi j equals to 0. Therefore, the equation reduces to kappa cos theta equals to b alpha beta lambda alpha lambda beta. Now, the right hand side of equation number 8, that is b alpha beta lambda beta, is invariant, because b alpha beta is a covariant symmetric tensors of rank 2, and lambda alpha lambda beta are contravariant vectors. So, the inner product of them is invariant. So, b alpha beta lambda beta becomes invariant. That means kappa cos theta is invariant. So, we can claim that kappa cos theta is invariant, hence the theorem. So, this is the proof of the Misner's theorem. Now, from this theorem we get a very new concept about the surface geometry, that is the normal curvature of a surface. This kappa cos theta is denoted by kappa n, and this is called the normal curvature of the surface, where kappa n is nothing but the b alpha beta lambda alpha lambda beta. Now, we know that lambda alpha is du alpha ds and lambda is du beta ds, because these are the unit tangent vectors. So, they can be represented in this way. So, kappa n becomes b alpha beta du alpha du beta by ds square. Now, ds square is the first fundamental form of a surface, and we know that ds square equals to a alpha beta du alpha du beta. So, putting that value, we get equation number 10, that is kappa n equals to b alpha beta du alpha du beta by a alpha beta du alpha du beta. That means the kappa n equals to the second fundamental form by the first fundamental form. That means the kappa n is nothing but the division of the second fundamental form by the first fundamental form. So, this is the normal curvature, and from this equation number 10 we can easily see that this kappa n depends upon the directions of the du alpha du beta. It is very interesting, where alpha beta is running from 1 and 2, we know that one. So, now the normal curvature of a surface depends on the directions of du alpha and du beta. Also, the angle between mu I and eta j. Mu I is the principal normal vector of the curve, and eta j are the components of the surface normal vector, but these are the space components. So, the angle between mu I and eta j is pi by 2 minus theta. So, g I j mu I eta j is cos pi by 2 minus theta. That means, g I j mu I eta j is equal to sin theta. Now, we have this relation that kappa mu I equals to kappa g eta I plus b alpha beta xi I lambda alpha lambda beta. From equation 7 we got this relation. Now, multiplying both sides by g I j eta j, we obtain kappa g I j eta j mu I equals to g I j eta I and kappa g plus g I j eta j b alpha beta xi I lambda alpha lambda beta. Now, you see that in the left hand side of 11 we get kappa g I j eta j mu I and this value is sin theta. So, in the left hand side it is kappa sin theta. Now, g I j eta j is equal to 1. So, it is kappa g and g I j eta j xi I, this is equal to 0. So, the second term is equal to 0. So, therefore, we got, so as the previous discussion, g I j eta j equals to 1 and g I j xi I eta j equals to 0. So, we have kappa sin theta equals to kappa g. That means, geodesic curvature of a surface is nothing but the kappa sin theta. So, equation number 12 is kappa g equals to kappa sin theta. Now, if we square 9 and 12 and add, we get kappa g square plus kappa n square equals to kappa square. So, this is the relation between the geodesic curvature, the normal curvature and the curvature of the curve on the surface. So, this is one relation of these three types of curvatures. Now, another relation we shall get in the next slide. Now, in 7, if we multiply both sides by g I j mu j, then we get kappa g I j mu I mu j equals to g I j eta I mu j kappa g plus g I j xi I mu j b alpha beta lambda beta. From 7 we get this relation after multiplying by g I j mu j. Now, since g I j mu I mu j equals to 1 and g I j eta I mu j equals to sin theta and g I j xi I mu j equals to cos theta and b alpha beta lambda beta is denoted by kappa n. So, we get another interesting relation between kappa g and kappa n, that is kappa equals to kappa g sin theta plus kappa n cos theta. So, this is a very interesting relation between the curvatures of the curves on a surface which have the same tangent vector, the kappa g that means the geodesic curvature of the surface, and kappa n, that is the normal curvature of the surface. So, in section 1 of module 2 of chapter 9, we have learned about Misner's theorem, and we have also obtained two relations between the curvature of the curves on a surface which have the same tangent vector and the geodesic curvature of a surface and the normal curvature of a surface. Now, in the next section we shall prove another very important theorem for surface geometry, that is Theorema egregium of Gauss, which was given by Carl Friedrich Gauss, a German mathematician, and this one is the relation between the Gaussian curvature of a surface and the first fundamental form of a surface. Actually, he has proved that Gaussian curvature only depends on the first fundamental form of a surface and their first and second order derivatives. So, let us see the Theorema egregium of Gauss and its proof. So, let us see the Theorema egregium of Gauss. This theorem states that the Gaussian curvature K is an intrinsic property of a surface which depends only on the coefficients of the first fundamental form and their first and second derivatives, but independent of the second fundamental form. So, in our earlier chapters we have defined Gaussian curvature as R1212 by A. So, in this theorem we shall prove that one actually, that why this Gaussian curvature is coming to R1212 by A. Now, see, from Gauss equation we have derived, that is also in our earlier chapter, that Gaussian curvature can be written by B by A, where B is the determinant of the second fundamental form, that is B11 B22 minus B12 square, and A is the determinant of the first fundamental form, that is A11 A22 minus A12 square. We have obtained this relation earlier from the Gauss equation in the previous chapter. Now, B, just I have mentioned that B is the determinant of B alpha beta and A is the determinant of A alpha beta. Obviously, A should not be equal to 0. And also from Gauss equation we have this relation R alpha beta gamma delta equals to B alpha gamma B beta delta minus B alpha delta B beta gamma. So, we have obtained this relation from the Gauss equation, and we have also obtained that this equation has only one independent form or independent equation, and that is B11 B22 minus B12 square equals to R1212. That means R1212 is nothing but the B11 B22 minus B12 square. Now, this R1212 is the 0,4 tensor, the Riemann curvature tensor. We have obtained these relations earlier. That means this R1212 can be obtained only from the first fundamental form of the surface with the derivatives, first order derivatives and second order derivatives from the Christoffel symbols. So, B11 B22 minus B12 square can be replaced by this R1212. That means the Gaussian curvature is nothing but R1212 by A. That means the Gaussian curvature depends only on the first fundamental form A alpha beta and their first and second derivatives, and it is independent of the second fundamental form. So, we do not need the second fundamental form to get the Gaussian curvature, and that is why we have defined earlier the Gaussian curvature as R1212 by A earlier. Hence, this theorem is proved. So, in module 2 of chapter 9, we have learned two very important theorems on surface geometry. That is, the first one is Misner's theorem and the second one is theorem egregium of Gauss. From the first theorem, we have also obtained a very interesting concept about the surface geometry, that is the normal curvature of a surface. We got two very interesting relations between the normal curvature of a surface, geodesic curvature of a surface, and the curvature of curves which have the same tangent vectors, that is also in the surface. So, from theorem of egregium of Gauss, we got the concept of the Gaussian curvature, and we have seen that Gaussian curvature only depends on the first fundamental form and their first and second order derivatives. With these two theorems, we end this module.